Hey everyone! So, when it comes to geometry, you've probably learned how to do a bunch of constructions, right? But have you ever stopped to think about why they actually work? I mean, really work, every single time. That's what we're digging into today. We're going beyond the steps and into the proof.
Okay, so here's our game plan. We'll kick things off by talking about what it even means to justify something in math. Then, we'll get our hands dirty with a classic example, copying an angle. From there, we'll actually build the proof, step by step. And finally, we'll see how all this stuff lets us build even cooler shapes.
All right, so let's get right into it. Think about it this way. In math, especially geometry, just following a recipe isn't good enough. You have to prove, really prove, that the recipe gives you the same perfect result every single time. That's what a justification is. It's our guarantee.
So, to be super clear, a justification isn't just some casual explanation like, oh, it looks right. No way. It's a formal, rock-solid proof. It's the logical argument that shows our construction method is legit and actually does what we say it does. It's all about logic. No guesswork allowed.
Okay, enough talk about abstract ideas. Let's make this real. We're going to take this whole concept of proof and apply it to one of the most basic, fundamental constructions you can do. This is where the theory hits the road.
So here's our mission, should you choose to accept it. We're going to prove that the classic compass and straight edge method for copying an angle actually works. We need to show, without a shadow of a doubt, that the angle we create is a perfect clone of the original.
Okay, so every proof has a starting point. We call it the given. It's the stuff we already know is true. In our case, it's this angle right here, angle ABC. Our one and only goal is to make an exact copy of it somewhere else.
All right, so here's what we do. First, we stick the compass point on B and swing an arc that cuts across both sides of the angle. We'll call those points D and E. Now, here's the really important part. Without changing the compass width, we go over to our new starting point S and draw a similar arc, creating point T. See how we're setting up a framework here? These steps are the foundation for our entire proof.
Okay, so we've done the physical steps. Now comes the fun part, the brainy part, building the logical argument that proves we did it right. Let's break this down one logical piece at a time.
We're going to use what's called a two-column proof. It's a classic for a reason. It's super organized. On the left, we make a statement. And on the right, we have to back it up with a solid reason, a definition, a rule, something we already know is true. You can't just say something. You got to prove it.
First up, statement 1. We're just laying out what we know from the get-go. We were given angle ABC, right? And because we use the exact same compass setting to make those first arcs, we know that all those little segments, BD, BE, ST, and SR, have to be the same length. They're congruent. The reason? It was given to us by the way we did the construction.
Next up, statement 2. Remember that last step? We actually measured the distance from D to E with our compass. Then we took that exact measurement and used it to mark a point R from point T. So we know for a fact that the segment DE is congruent to the segment TR. How do we know? Again, by our construction method. It's another given.
And now for the first big aha moment. Let's just imagine we draw lines connecting D to E and T to R. What do we have now? 2 triangles. And check this out. We already proved we have 3 pairs of matching sides. BD matches SR, BE matches ST, and DE matches TR.
So why is that a big deal? Because of something called the side-side-side postulate, or just SSS for short. This is a fundamental rule in geometry. It basically says if you have 2 triangles, and you can prove that all 3 sides of one triangle are congruent to the 3 sides of the other, then the triangles themselves are identical. They're exact copies. And that, my friends, leads us to the grand finale. Since we just proved that our 2 triangles are totally congruent, well, that means all their matching parts have to be congruent too. And that includes the angles. So the angle at B has to be congruent to the angle at S. And just like that, we've proven our construction works. It's justified. The magic reason behind that final step is CPCTC. Yeah, it's a bit of a mouthful, but it's super powerful. It stands for corresponding parts of congruent triangles are congruent. It's the ultimate payoff. Once you do the hard work of proving triangles are congruent, you get to say all their other matching bits and pieces are congruent too. It's awesome.
So you might be thinking, okay, that was a lot of work for one little angle, but here's why it's so important. That justified construction is now a tool we can trust completely. It's like a perfectly calibrated instrument in our geometry toolbox, letting us build way more complex stuff with total confidence.
Take constructing a regular polygon, for example, like a perfect hexagon.
To do that, you need two things. All the sides have to be the same length, and all the angles have to be the same measure. And how do you guarantee the angles are the same? You use our just proven method for constructing congruent angles. See, it's a building block.
And you can even stack these proven methods on top of each other. Let's say we use a justified method to make a perfect 90-degree angle. Cool. Now we can use another proven method, the angle bisector, to slice it right down the middle. What do you get? A perfectly accurate 45-degree angle. Every step is built on a foundation of solid proof.
So that leaves us with a cool question to think about. We've seen how to copy an angle and how to get a 45-degree angle from a 90. If you keep using these tools, bisecting angles again and again or combining them in clever ways, what other precise angles do you think are possible to create? The cool thing is, whatever you can make, you can prove it's accurate, all thanks to the power of the logic we've talked about today.